Hello everyone and welcome to this video. So I want to take off here in this video where we left off in the last video, which was just reviewing the Laplace transform. So what I want to do is now talk a little more about the table, or at least draw out the table a lot more. Draw the table and let's at least get used to working with the table. Okay, so we have a time function on this end, and then we'll have our Laplace transforms on the right. So a couple of functions that are quite important to us, particularly when we're dealing in control engineering. And the first of them is, we call this the Dirac delta function. Dirac delta function. Okay, so maybe I should put name in here. For those that have special names, I'll write their names here. Okay, so this is called the Dirac delta function, and it's actually, if you want, our impulse, our unit impulse function. UNIT. Okay, unit impulse function. Maybe I should rewrite that. Unit impulse. Okay, so when you have the unit impulse function, the Laplace transform of that is simply 1. So the Laplace transform of the unit impulse is simply 1. We already encountered this in the last class. This is the unit step function. Okay, so that's a unit step function, and we know the Laplace transform for that is 1 over s. We have this other function. If we multiply the unit step function by t, okay, if we multiply the unit step function by t, then this is called unit ramp. A unit ramp function. Now, if it helps, let me kind of try to sketch what these functions look like. I apologize, the space I left here is quite small. Maybe I should draw them on the right. The Dirac delta function is a function that has no value, has a 0 value for time less than 0. At time t is equal to 0, it has an infinite amplitude, and at time t greater than 0, the value once again is 0. This is your Dirac delta function. At the time t is equal to 0, it has an infinite amplitude, but then it is 0 everywhere else. Our unit step function, we already said, is 0 until you get to time t is equal to 0, and then the magnitude now becomes 1. Our unit ramp function is 0 when time is less than 0, and at the point where time becomes 0, it starts rising and keeps on rising. The differential of this graph is simply 1, so it rises at a rate of 1 unit amplitude per time. So if you check this out, when t is equal to 1, the amplitude will be 1. When t is equal to 2, amplitude will be 2, like that. Okay, so it rises continuously. So this is a unit ramp function. The Laplace transform for this is 1 over s squared. Okay, 1 over s squared. Now, let me write one more function. You have t squared u of t. Now, this is an acceleration function, or a parabolic function. It doesn't have a special name per se, but let me call it a parabolic function. Parabolic. If you want, you could call it a unit parabolic function. And the Laplace transform for this, I believe, is 2 over s cubed. Okay, I believe it's 2 over s cubed, and it looks okay. So it's 0 as time, when time is less than 0, and then it starts rising with a square law. It starts rising with a square law relationship. Okay, so it's the square of the time. So it rises like that, and that's probably the last function I would draw here, and I'll probably give a name to. So let's have an exponential function that we had in the last class, e to the power minus at, again multiplied by our unit step function u of t, and we have that as 1 over s plus a. Then let's now have sinusoidal functions. We had this again in the last video. Sine of omega t, u of t. This is a sine function, and this comes out as omega over s squared plus omega squared. And then our cosine of omega t, u of t, is s over s squared plus omega squared. Okay, so those are the Laplace transforms. This is the basic table that we typically tend to have, and So that's the basic table that we typically tend to have. I decided to draw this largely because I wanted to mention these functions, the direct function and the ramp function, just to give you those names. We will encounter these a little more a little later. Now, having said that, there are some rules that we tend to follow when we're dealing with the Laplace transform, or some theories if you want, and this just make life a whole lot easier. They make life a whole lot easier. So let's say we want to find the Laplace transform of a constant multiplied by f of t. So maybe to do this, it will help if I first of all write the fact that the Laplace transform of f of t, lowercase f of t, is f capital uppercase f of s. S is lowercase. We know the definition for this. Okay, so let's say that the Laplace transform of f of t is equal to that. If I take k, just a constant, and multiply it by this, the Laplace transform of this will be that constant multiplied by f of s. If you want to take an example, if you're told to find the Laplace transform, you're told to find the Laplace transform of 2t, then remember what the Laplace transform of t. Okay, so 2t u of t. Let me include the u of t here so that there's no confusion, no ambiguity at all. Okay, so we're told to find the Laplace transform of 2t u of t. If you go back up and you remember that the Laplace transform of t u of t is 1 over s squared, then we know that the Laplace transform of t u of t is 1 over s squared. We have a constant 2 multiplied by that. So in other words, our answer will be 2 multiplied by 1 over s squared, which is simply equal to 2 over s squared. Okay, so a constant multiplied by a function gets a constant multiplied by the Laplace transform of that function. If we have two functions whose Laplace transforms we know, so f of t, let's say f of t and g of t. If we know the Laplace transform of f of t and we know the Laplace transform of g of t, then if we have this sum, the Laplace transform of this sum will simply be the Laplace the sum of the Laplace transforms. So that's okay, f of s plus g of s. You could take an example. Let's say you wanted to find the Laplace transform of, and now I'm sure I'll run out of space quickly, Laplace transform of minus 2t plus sine 2t. If I told to now just assume this is all multiplied by u of t, if I told to find Laplace transform of this will simply be equal to 1 over s plus 2 plus 2 over s squared plus 4. How did I get this? Use the table that you have above. E to the power minus 2t, you have 1 over s plus 2, and this sine omega t is omega over s squared plus omega squared. So that's how I get this answer over here. Okay, so that's the second theorem that we have. Third theorem. Now, you remember that this is defined as an integral from 0 to infinity of e to the power of minus st multiplied by f of t dt. Now, because this is an exponential function, this next theorem makes a lot of sense. That if you had an exponential function, say e to the power of minus at multiplied by f of t, okay, multiplied by f of t, if you think about this expression here, it makes sense that what you will now have will be e to the power of minus s plus at multiplied by f of t. That effectively is what you will have in here, but the Laplace transform of this will simply be f of s plus a. Okay, f of s plus a. So, okay, let's take another example over here. And I do apologize, I probably have not used my space very well. Maybe what I'll do is not just complete, yeah, let's just go on. So, Laplace transform of e to the power of, say, let's use the same example, minus 2t, but this time multiplied by sine of 2t. Okay? Now, let's assume our sine 2t is our f of t. If our sine 2t is our f of t, then Laplace transform of this should have been 2 over s squared plus 2 squared, right? That is omega over s squared plus omega squared. However, because we have it multiplied by e to the power of minus 2t, okay, our theorem says that now we'll have of f of s plus a. So wherever we have s, it will no longer be s, it will now be s plus a. So instead of having this as our solution now instead will be 2 over s plus 2 squared plus 2 squared. I hope you get that. Where s was supposed to be, now we have s plus 2. So that this is simply equal to 2 over, well, maybe not simply, 2 over s squared plus, that should be 4s plus 4, then plus 4. Okay, so all of this here is our s plus 2 squared, now plus 4. So our final answer is now equal to 2 over s squared plus 4s plus 4s plus 8. Okay, 2 over s squared plus 4s plus 8, and now this is our answer. And all we've done is we've used this well, we've used a bunch of rules together. Okay, we used a bunch of rules together and we've come up with our answer. Okay, let's pick our next theorem. Our next theorem is called, if you want, it's called the time scaling theorem. So this previous theorem we just dealt with here, this one is called the time shift. Okay, the next one we want to deal with is the time scaling theorem. Let's say we want to scale our time. Okay, so let's say we want to find the Laplace transform of f of a t. So this is scaling our time. Okay, so we're multiplying our time by something. So this is scaling our time. The Laplace transform of this will be equal to 1 over a f of s over a. Okay, we could take an example of this, but I don't want to. Well, it's just kind of straightforward. It's okay. So if you have, well, okay, let's just pick an example. Let's say we're told to find the Laplace transform of e to power of. Let me actually use minus minus 2t. Okay, if I use this as minus 2t, so this assumes that in this case my f of t is equal to e to power of minus t. Now if f of t is equal to e to power minus t, what is the Laplace transform? The Laplace transform of that is simply 1 over s plus 1. Okay, that's 1 over s plus 1. If this is my function, Laplace transform of this is simply 1 over s plus 1. Now, if we're going to use this rule, the time scaling rule, then it says that the Laplace transform of this should be equal to 1 over 2 multiplied by f of s over a. So that is now 1 over, instead of having s, I will have s over 2, then plus 1. Wherever s was, we'll replace that by s over a. A in this case is 2. So we have this expression. And then multiply this out. What you end up getting is 1 over s plus 2. Now, if you just were told to find Laplace transform of this, what do you expect to get? This is exactly what you expect to get, and that is exactly what we get. Okay, now so I'll stop this recording at this point, and in the next video I'll go on with the theorems, and we'll go on to differentiation and integration in the next video. Thank you.